In this lecture, which is week 6 lecture for Geography 136, I'll be talking about different methods for raster data analysis specifically. The last few weeks we've been talking about different ways to analyze or get new information or derive data from vector data. And now we're switching gears a little bit and looking at raster data. In future weeks, we'll look at a couple different ways where you can combine different layers together, whether they be raster or vector, and solve spatial analysis questions with either type of data kind of put together. But for today, we're looking at raster analysis. This lecture is going to be split into 3 videos, but these correspond to 2 overarching themes. The first of these is just going to be a quick introduction to the raster data model. This is mostly going to be review. There's a couple slides that are kind of review from our earlier overview of key topics in GIS. And then I'm going to be talking a little bit more about some more specifics of raster data that are important to consider and to know about when kind of choosing to set up a project with its basis in raster data versus vector data, and to just know the strengths and weaknesses of conducting analysis using raster data. Then the second part is going to be split into 2 videos, and these 2 videos will focus on specific analysis methods that are grouped according to several different categories. So the first video is going to be about local analysis methods. So when we do raster analysis, you can conduct local analysis or local operations on that raster data. There's a whole bunch of these and a few kind of broader topics to cover before talking about these raster analysis methods, so that'll be the first video. And then the second video will focus on these other subcategories of raster analysis methods that include neighborhood analysis, which is often also called focal analysis, zonal analysis, and global analysis or global operations. And we'll talk about each of these in turn. The reading for this week is Chapter 12 from the Chang textbook, Introduction to Geographic Information Systems. So this will be accessible on Canvas to you. Okay, so first a review of these main 2 types of data models. So far, for the most part in this class, except for that early review lecture, we've been talking about vector data and analyzing vector data. Vector data is that data made up of points, lines, and polygons. Each of these are kind of described by either the coordinates of a given point or the coordinates of points that kind of connect as vertices to make up these larger features of either lines or polygons. At right, again, as a review, we have trees that are illustrated using this vector data model. At the far right, trees are shown as polygons. We have a whole bunch of different kind of tree-shaped blobs shown in green on this street. These are vector data. These are polygons showing the outline of where a tree is or where the canopy of a tree is. Then just to the left of that, still kind of in the upper part of the right part of this figure, there are trees that are instead represented by points. So here we have a number of different points. They kind of have varying widths, so they're visualized according to the actual size of that tree. However, they are points. They have one single location in space, and we have circles visualized for those specific points of where all those trees are. Again, raster, overall, the underlying idea is that it's made up of rows and columns of equally spaced grid or cells that represent a phenomenon. So at left, we have a raster representation of areas that have predominantly trees. So areas that are mostly trees are shown in this dark green pixel by pixel. So each of these little squares, when you zoom in, will say whether it's mostly trees there or a forest, or whether it's mostly something else like urban or agricultural or something like that. So let's zoom in a little bit to the characteristics of what raster data looks like when you actually zoom in closely into one of these layers. Raster data is a continuous surface, or sometimes called a field of data. Each data set really only represents one characteristic of the world and how it varies over space. It does this by representing the world as a number of cells that are laid out in rows and columns over the extent of the data set. It's usually the preferred data model for phenomena that are continuous in the real world. Continuous meaning they vary over space. Everywhere you go, there's a slightly different value. No matter how small your movement is in space, there will at least theoretically be a different value in that location. A really common example, of course, is elevation. At right is a model showing how elevation data is transferred to one of these raster data sets. Each of these cells is coded by the elevation of that location. The dark green cells or squares that would show up in your raster data are larger values for elevation. Those white areas are in a valley. They're lower elevation areas, and they're coded as such on the map. But if you look at the actual values within each of these cells, it would look like something at left, where you have a single value that sums up, on average, what the phenomenon is for that cell. So again, another good example of a good use case for raster data is for something like pollution. If you have a source of pollution, like a factory kind of emitting pollution into the air, it'll be highest at that point, right where the air pollution is being emitted, and it'll diffuse out into the air, progressively becoming less as you move away from that source of pollution. So it's a really good way to convey that diffusion of something like pollution through a medium like the air. That'd be really hard to convey in vector data, right? So you can't just like wrap a polygon around different levels of pollution very easily, because it continuously varies in space and it changes as you get further away, but there aren't really kind of like well-defined categories of where has pollution, where doesn't have pollution. So a few more specific characteristics going into more detail about how these rows and columns of equally spaced cells translate into raster data. So they're made up of rows and columns, and these rows and columns start in the upper left. So this is different than when you're looking at like a graph in the math world where we have the origin at the bottom left. Instead, when we're looking at raster data, we typically define the origin as the top left. And we define X location as the column that the cell belongs to, Y location as the row that the cell belongs to. And then again, generally cell height and width are generally equal. So these are usually squares. It's possible to create a raster that doesn't necessarily have square-shaped cells, but that's really uncommon. For the most part, the X distance for each cell and the Y distance is going to be exactly the same. Then the extent is the word describing the four corners of a data set. Because each of these cells is going to be square, the entire data set's usually square or rectangular. It's usually not kind of an amorphous blob unless you conduct some analysis that makes it that way. So the extent is from one corner to the next corner, to the bottom left corner to the bottom right corner. So when you're defining the extent, usually there's 4 different coordinates to enter. And just going back to talking about cell height and width, we often talk about cell size or pixel size. We just refer to one of those values. So if one cell, the X distance of that cell is 30 and the Y distance is 30, we usually refer to that pixel or cell as being a 30-meter resolution cell. The data set overall is referred to as a 30-meter resolution data set. So that gets us to the topic of spatial resolution. It's really important to clarify and touch on just briefly. But spatial resolution, again, is that cell size. High resolution means small cell size. That means there's a lot of cells in your data set compared to the area that you're covering. Low resolution means large cell size. So for each cell covers more area, but there's less spatial information and less spatial detail. So there's a couple pluses and minuses of working with each of these types of data, either high resolution or low resolution. I mean, generally you want as high of resolution as possible, but of course there are drawbacks too. So while high resolution has really a lot higher accuracy and precision, it can be slower to display, slower to process, and it can take up a lot of memory too. So for my PhD work, I had a whole bunch of raster data sets that I digitized, and these are basically all just like massive images. And each image that I had to digitize and put together eventually was over a gigabyte in size. So that makes it really difficult to have, several dozen gigabyte plus size files that are central to your analysis. Because if you have to move those, it's not easy to do that over the cloud always. I was using Google Drive, so I usually had to use thumb drives and not Google Drive because the sizes were just too big to easily upload them and then download them again through the cloud. Low resolution, again, has large cell sizes, which is generally not good for accuracy and precision and really representing your phenomenon well, but you do get faster processing and display. So it doesn't always make sense to use as high a resolution as possible. Sometimes there are constraints in storage or processing or time that it might just make more sense actually to prefer lower resolution data. So on this slide at the left, we have a polygon that's, again, in that vector data model. This is a whole bunch of connected points that are called vertices that make up this kind of blobby feature. If we look at that in the raster world with high resolution, we have 1 meter cells. That gives us 16 by 16 cells, 16 rows and 16 columns. And you see that the cells filled in to represent that polygon do a pretty good job of approximating the shape of the polygon. But as we move to lower resolution, and we move to 2 meter cells and then 4 meter cells at the far right, the actual shape of that real world object gets really simplified and abstracted. It does a lot less good of a job at showing what that original polygon was at the far left. So again, at the far right, we just have 5 large cells kind of filled in to represent the general blobby shape of the original blob that was much more, much smoother and rounder instead of just kind of like 5 squares put together. And kind of expanding more on one of the other earlier points, data in a raster data set is held as a single value for each individual cell. That's kind of a foundational property of raster data. That single value, whether it's air pollution or elevation, or just on the last slide, like whether the blob exists there or not, it can either be applied to the center of the cell, or it can be considered to be the value in the whole cell. So there's a couple different ways of kind of conceptualizing what that value actually means. And those are shown on the right of this slide. So if we have the value applying to the center point of the cell, then what you're really getting is kind of this smooth surface where it's presumed that the rest of the cell is connecting, according to some mathematical algorithm, to the boundaries of the cells next to it. That everywhere within that cell is actually varying over space as well. We're just not able to portray that. But at the bottom, if we're conceptualizing this as that the values apply to the whole area of the cell, we're kind of conceptualizing it as this stepped feature like you see at the bottom right, where there's actually kind of vertical differences. We're ignoring that subtle variation as one cell kind of moves into the cell next to it. Now, using either of these, rasters can hold a variety of data types. So it's not just like a simple single number, like those examples at right. The numbers can be floating point. When we talk about floating point data, we're talking about data that has a decimal attached to it. Often we use the data type double. That's just a long floating point value. The data can also be integer, like the examples at right. That's where we just have whole numbers representing the value for that entire cell. Values can be positive or negative, and you can also include no data values. So instead of just saying like 0, you can include a value that's just either coded as like -99 or -1. If those are outside the actual range of the data set, you can punch those in and say these actually mean no data. Nothing actually exists there. We don't have data for that. It's not a 0. So with this flexibility, raster data can represent all sorts of real-world phenomenon. So the cells can be used to represent something like the average within that area. So we might have a big cell that has average income within that entire area. It might represent the central point, like with elevation. So for a given cell size, we're saying that point in the middle of it, right in the center of that cell, the number for that entire cell represents the elevation at that point. We can also have categorical values like land cover, or just whether something exists in a place or not. So land cover, we could have like a map where we have coded values where like 1 equals urban, 2 equals forest, 3 equals water, etc. Or we can have like a buildings layer where each cell is coded as 1, where there is a building there, or 0, there is not a building there. So even though we can only put numbers into these cells, we can represent nominal categories or categorical values. Even points, lines, and polygons can be represented. So a lot of times you might take a vector data set and convert that to raster. Again, these will usually be represented as a binary layer where either the thing exists in that place or not. So you might have a cell with a tree in it. You'd code that as 1. If the cell next door didn't have a tree in it, you'd code that as 0. So again, you might lose some specificity and you might lose some precision because you're just saying that there is at least one tree within this cell, whatever the cell size is, rather than saying exactly where the base of that tree is. Then, like the point, line, and polygon data that we talked about before, raster data does have attribute data attached to it. So if you're in ArcGIS and you open the attribute table for a raster data set, you will see an attribute table. However, what it looks like and what properties and numbers and fields it contains, all of these will differ from what you saw with vector data. With vector data, there's what's called one-to-one data storage. That means that there's going to be an entry for every unique feature. But in a raster data set, this would mean each entry would have an entry. Every single pixel would have an entry, and that just becomes meaningless really quickly because, again, even the smallest raster data set is going to have hundreds or thousands of cells. It wouldn't really be feasible to have an entry for each of those cells, and it wouldn't even really be meaningful because all those cells contain is that one value, that one quantitative value at that cell. So rasters in the attribute table use what's called many-to-one data storage. That means many raster cells refer to a single row in the attribute table. Data is organized by cell value. Usually what you see is the number of cells with a given value shown. So you just get like a cell value and then a count for that value. That's seen at the bottom left right here. So we have a value of 1001, 1002, 1003. Those are the actual numbers in each of these pixel cells. And over this hypothetical raster data set, so there's 1,574 different values that are represented. If you break that down and look at just these values like 1001, you can see that there's 1,857 instances of a cell that has a value of 1001. This isn't that useful for quantitative values like elevation. This doesn't give you a whole lot of information, but it can be really useful for categorical data. So it basically tells you the number of cells in each category, and that allows you to calculate the total area of that category. But it's not that useful for continuous ratio or interval data as we've seen. So like elevation, it doesn't really matter how many cells have an elevation of like 312.2 meters versus 312.4 meters, which you'd get a count of each of those, but that doesn't really mean anything. Again, with land use or land cover or other categorical variables, it can be pretty useful. So the figure in the top right shows an attribute table related to a raster where there's just 3 different categorical values representing land cover. We have a river, it looks like, represented as number 2. These are technically coded as water, but it's kind of a linear feature in raster form. We see that there are 11 cells coded as water, 23 is barren land, and 8 is forest. So if we knew the pixel cell size, we could pretty easily calculate the area of each of these within this scene, which is pretty useful. More of a real-world example is shown in the bottom right. We have these NLCD classes, so that's that National Land Cover data set I've talked about before. And for each of these classes, we have the class value, so that's what will actually show up in the raster layer itself, either 11, 21, 22. These are just codes for those NLCD classes at the far right. But then for each of those, we get a count, so we can see what land cover type makes up most of this scene that we're looking at. And in this case, if you look at the count, it looks like developed, open space is the most prevalent land cover type, and then developed low intensity is most common after that. So all of this kind of summed up is to say that the analysis potential for raster data is really in the cell values themselves. You're actually looking at that spatial display and looking at the numbers in each of those cells. And it's a much more, in some ways, a much more visual exercise analyzing raster data, because you're putting these numbers together in different ways and then looking at the outputs related to the actual numbers that show up in each of these cells. So just kind of a summary of the advantages and disadvantages of raster data for analysis specifically. The simple structure overall is really helpful in analysis. All those values are held in just one file that's really just a grid. The numbers are clearly, straightforwardly connected directly to those cells and their location. Then this also allows for really powerful analysis capabilities. It's really easy to combine raster layers. Cells of different data layers generally align spatially, so you can conduct operations between these overlying cells. And these operations are really fast, so you can kind of do a whole bunch of complicated analysis steps together pretty quickly. There are no geometry changes, like when you're working with vector data. A lot of times you have to clip polygons or something like that, and you actually change the geometry. A lot more recalculation has to go on spatially. Then the capabilities are really strong for representing continuous phenomena specifically. So these are those things that vary over space no matter where you go. Things that change frequently are really well represented because you can see really subtle changes over space in these things, rather than with vector data basically having to classify them and say, like, this is a really high area, this is a slightly lower ring around that, this is an even lower ring around that. You can get the actual values as they vary over space to a very precise level. Finally, they're really useful data for digital image data. Again, I even now kind of interchange the words pixels and cells. Usually when you're talking about like digital imagery and remote sensing imagery, you talk about pixels. When you're talking about like rasters that are just coded with something like elevation, you talk about cells. This type of data is so fundamental to the display of digital images that I often mix these things up. But really, when you are looking at like a satellite image, just the reflectance of the image is shown in each of these cells, which is then called a pixel. That works really well for just displaying a digital image. Of course, there are disadvantages as well. As I talked about a couple slides ago, data sets can get very large because that data is stored everywhere in a layer. It's not kind of linked to just a document that's basically made up of text. Then the accuracy is also limited by cell size. So if you have larger cells, the accuracy is pretty bad. So again, the example of like a tree in a raster cell, the spatial location of that tree, you can't get very precise because you're just saying it's somewhere within this cell. Related to that, for discrete objects other than trees, where the discrete objects are actually bigger than an individual cell, you get these stepped outlines. So again, like that blob I talked about a couple slides ago, or like a building, if you're trying to represent that in raster form, you won't get the smooth, straight line boundaries that you'd actually expect for that feature. You'll get a pretty decent overall representation of where that feature is in space, but the shape of it won't look quite right because you have to represent it by these grid cells, the square features, that a whole bunch of these square features together making up this thing will look different than just a straight line connecting two dots as you'd see with vector data. All right, so those are just some basic considerations in using raster data and a little more about the details of what raster data actually contains. And now in the next couple of videos, I'm going to talk about raster analysis methods that can be really useful for learning new information about the world or analyzing data, putting different layers together to get, again, new information.